Hello, everybody. So cool, I'm still waiting for this presentation to appear on YouTube. Yep, here we go. I can see it live right now. And I can hear myself. I hope everybody else can see the slides and can hear me. So cool. I can see that some viewers started to come and to show up. So let me just start by saying hello, everybody. And excuse me. And wishing everybody a happy Valentine's Day tomorrow. Let me just grab a sip of water before we start. Whew. Sorry for this difficulty, although it's not technical like what happened last week. But we should face some difficulties every week. Anyways, it's 3 o'clock now. Welcome to our 5th meetup or webcast of the year. Today we're going to talk about self-repair and self-reproduction modular robotic systems. Before I start, I would like to wish everyone a happy Valentine's Day one more time, because I just did, but I'm going to wish it again for the newcomers who just joined our video or our webcast. So please, if you don't have a significant other to love your science, love your projects, and feel free to share them with us. Because we want to hear from you. So please contact us if you would like to talk about a project, research idea, research method, or just anything cool you'd like to share. We need you and we want to have you involved. So today I have some good news to share. If you like our previous meetups, you can find the summary of all the previous meetups, including this one of today, in a paper that I published on archive.org. And I'm going to publish the URL in the description of the video after finishing this webcast. So please feel free to navigate to this URL and check the paper out and let me hear from you. I want to get your feedback, your comments about this paper in order to make it better and write better research papers in the future. So today, we're going to cover these topics. Introduction, self-repair robots and their applications, self-reproduction robots, their classes, some literature review, and their applications before concluding. So the reason for combining 2 different topics in one webcast is that there wasn't enough research that was done in the self-repair robotics field or the self-reproduction robotics field. That's why in order to have enough topics that we can cover in our 30 to 45 minutes webcast, I just decided of combining 2 similar topics in one meetup. So let's start. Modular robots involve various modules that can combine themselves autonomously into a meta-module or a structure that is capable of performing a specific task under certain circumstances. In the last meetups, we mentioned that modularity benefits include the capability of self-assembly, self-reconfiguration, and today we're going to cover self-repair and self-reproduction. So what are the benefits of self-repair and self-reproductions? Now we're going to see. And we will start by discussing self-repair robots. So the self-repair is a special type of self-reconfiguration, which we discussed in our last meetup, that allows a robot to replace damaged modules with functional ones in order to continue with the task at hand. So each modular robot will have some spare modules. In case of a failure or a problem, it can eject the damaged module and replace it with a fresh, fully functioning one. Such robots are well suited for working in unknown and remote environments. So let's check the applications. So the first application we're going to discuss is TEBot. And we talked about TEBot earlier in the modularity meetup. But today we're going to discuss self-repair and how it can be performed in TEBot. It actually can be performed in TEBot with a simple procedure due to the layered structure of the system. So the strategy is to transport spare units to the area of the damage and refill it. This self-repair can be performed by degeneration of the system to the previous stage, which is the same location index as the removed unit. So this system saves the stages, and every time a failure happens, it will go to the previous stage before this failure occurs. So there are many types of failures to be considered. The researchers who made TEBot dealt with only one category of failure, wherein some units are removed from the system, assuming that the remaining units work correctly. The removal may include several units and may occur at any place in the system at any time. So not only the units on the outer surface, but also the ones inside of the logical network may be removed if the remaining units are connected. So they assume that all the units are connected. The self-repair method they proposed consists of 3 steps. Number 1, failure detection. Number 2, degeneration signal. And number 3, degeneration. Failures can be detected by the units involved in the connection network. If a defected unit does not respond to a signal from an active unit, degeneration signal is transmitted by the units that have detected failure, and the signal is propagated to the overall system. This signal includes the level of the failure, which is the location index of the removed unit. The level of the failure determines the stage to which every unit should return. After the transmission of a degeneration signal, the system returns to a specific stage determined by the minimum location index of the removed units. If several failures occur in the system, signals of several levels are spread, and the system goes back to the lowest level. So we must note that if the kernel is removed, which is the basic seed of the system, the units must begin again with the kernel selection process. So they will start building a new robot from the ground up. The authors also considered the simplest case that several units are removed from the system and the remained unit work correctly. They did not mention the other types of failure, such as halting failure, in which failed units do nothing. So they did a great job, but I really wish that they continued working on the same prototype, which is TEBot, in order to address different types of failures, so they can cover like different perspectives Do you guys agree with me? Or shall we move to the next application? Oh, I guess you do agree. So let's move to Fractal. So Fractal, we mentioned it as well earlier in the modularity meetup. It's a hardware system composed of 20 mechanical units. It was used for validating a simulated annealing algorithm for self-repair robots. The researchers who made Fractal considered self-repair as an extension of self-assembly. We mentioned earlier that self-repair is a special case of self-reconfiguration. However, the researchers who worked on Fractal, they considered self-repair as an extension of self-assembly that detects damage and let the whole system reconstruct itself. As in Fractal's self-assembly process, each unit has the same software, decides its movement only according to local information. Computer simulations showed the effectiveness of this method using a system with more than 10 units that successfully reconfigured themselves and recovered from a fault. That's really cool. And again, I would love to see more. I would love to see a physical system that can reconfigure and recover from a failure. But overall, great job. Again, if you have any questions, please feel free to ask before we move to the next application, which is Crystalline. So, Crystalline can self-repair using a 3-phase process, similar to what we mentioned earlier in TEBot. However, this process is so different than TEBot, so let's see how. The 3-phase process of self-repair in Crystalline is as follows. Number 1, detect failure. Number 2, eject the failed module. Number 3, replace the failed module. So the researchers did not address detecting module failure. They might discuss it in like a different research paper that I haven't seen yet, but all the resources that I have does not include or do not include detecting module failure. They assumed, however, that a bad module might not be able to move under its own power. So the other good or live or fresh modules in the system should manipulate the dead module into a position for ejection. So they will manipulate it to move it into a certain location that can be ejected from. So the strategy to move the dead module to a place where it will simply fall off the robot when released by any attached live module depends on the design of each crystalline module that you can see in the diagram here, expansion and contraction. So the modules will expand and contract in order to push this dead module and then eject it. So their solution identify all locations on the surface of the robot from where it's possible to release the bad module and computes the shortest path to that region, and then uses a gate to propel the bad module along the shorted path. I think that's simple and clear. And this algorithm supports 2D, 2-dimensional models only. TD. I don't know where. Okay, whatever. I think in their future work, they mentioned that they're going to work on a 3D model. but still, I haven't seen it yet. I mean, to be honest with you, 2D is fair enough. And again, the process is very simple, and I guess it's effective. I'm a person who likes simplicity in everything, even in algorithms. So, I guess there are no questions, so let's move on to our next topic, which is self-reproduction robots. Self-reproduction robots. The ultimate form of self-repair is self-reproduction. And we mentioned earlier that self-repair is the ultimate form of what? If you can remember. Self-repair is the ultimate form of self-reconfiguration. Except in the case of Fractal. They consider that as the ultimate form of self-assembly. So let's get back to self-reproduction, which we consider as the ultimate form of self-repair. Self-reproduction allows robots to reproduce themselves from an infinite supply of parts using simple rules. If the resulting system is an exact replica of the original, then the system is called a self-replicator because it generated a an exact replica of itself. The effort in self-reproducing is focused on the design and construction of a small seed system that will grow exponentially to form a larger system through tens of generations. The resulting self-reproducible robots are capable of accomplishing very large-scale tasks, such as collection of solar energy, direct removal of greenhouse gases from the Earth's atmosphere, and water purification for irrigation. Self-reproduction differs from automatic manufacturing or self-assembly because the resulting system do not need to make copies of themselves in the case of self-assembly or automatic manufacturing. So since any replication process requires an external material supply, we always assume that some lattice positions may act as dispensers where new modules reappear when removed from that location. So self-replication is classified to the following types or classes. Direct reproduction, multi-parent reproduction, self-assisted reproduction, and finally, multi-stage reproduction. It's direct reproduction. In this class, a robot picks modules from a dispenser and places them in a new location to gradually build a copy of itself from the ground up. In the second class are multi-parent reproduction. Multiple robots produce a single copy, such that one robot places the modules while the other assembles these modules. In the third class, self-assisted reproduction, the robot being built self-reconfigures to assist its own building during the building process. And finally, in multi-stage reproduction, temporary scaffold is needed in order to build the target robot. Then this temporary scaffold is either discarded as waste or reused to produce additional robots. So now let's talk about some literature and let's review it together. So in the year of 1966, von Neumann was the first to prove the possibility of self-reproduction in his close to physical implementation kinetic, oh my god, I just said it right, kinetic model of self-reproducing automata, where he aimed to explore computing devices analogous to a human brain, in which the memory and processing units are tremendously parallel and are capable of repairing and building themselves given the required raw material. Then in 2002, Chirek-Jian and other researchers introduced the concept for self-replicating robotic systems composed of mobile robots, materials, processing unit, solar panels, and a railgun. Wow. These are a lot of components. Initial hardware prototypes were constructed from Lego Mindstorm kits, along with enhanced electrical connections and magnetic alignments to demonstrate direct replication. The Lego kits were used to reduce the complexity because of their modular nature and ease of use. They built two prototypes, fixture-based design and semi-autonomous replicating system. The first prototype is a remote-controlled robot that is not autonomous, but can produce a replica of itself. The second prototype is unable to make copies of itself directly. Therefore, the robot makes intermediate systems with different properties than itself. Then those intermediates can assist the original robot in manufacturing replicas of the original. And more recently, in 2005, Griffith and other researchers demonstrated that self-assembling systems, again we go back to self-assembly, can self-replicate if the intelligent modules were configured to duplicate. So the system can self-replicate by selecting the appropriate building blocks from parts distributed in the environment. Moreover, this system can self-repair the errors occurred during the copying process. I would love to see a physical implementation of the system. That's going to be awesome. So again, if you have any questions, feel free to type them before we move to applications. Just technically, one application. I told you today's meetup is too short because, I mean, a lot of research has been done, but still, compared to other fields, it's not much. So we can cover like 2 topics in less than an hour. So one of the biggest applications of self-reproduction robots is Somali Cubes. So Somali Cubes was introduced by Zykov and other researchers in 2007, which is an autonomous, self-reproducible robot that is composed of cubical building blocks. I think we discussed Somali Cubes earlier in, I think, the meetup of self-reconfiguration and modularity, if I'm not mistaken. So Somali Cubes are actuated modules equipped with electromagnets to selectively control the morphology of the robotic assembly. In order to self-reproduce, a machine requires a supply of material. The modular robots were supplied with cubes that were manually replenished at several feeding locations. The robot was able to construct a replica by lifting and assembling cubes from the feeding locations, because the replica because the replica is as large as the original. So the replica reconfigures itself to assist in its own construction. Any questions? Today our crowd is very quiet compared to the past meetups. Guys, come on, it's February. We just had the lovely snowstorm. Okay, I guess no questions or comments, so boom, conclusion. In this webcast, we've presented a review of modular self-repair and self-reproduction robotic systems that were created to meet three main goals: versatility, robustness, and low cost. If you have any questions, feel free. Oh, hey, Stefan, how are you? No problem. If you have any questions, feel free to ask them now, or here under the video in the YouTube channel, or in the Meetup website. If you have any suggestions, feel free to contact me directly. And don't forget to sign up for the hackathon and checking the paper on archive.org. And feel free to share your feedback with me. So before we wrap up, you have the link. Feel free to watch the video at your convenience and share it with your friends, and keep in touch. And again, happy Valentine's Day tomorrow. And enjoy the rest of your day today.